All right, talking about scientific notation, we will now use a common application of positive and negative exponents in scientific notation. This is a useful way of writing very large and very small numbers in a standardized way in which it is easy to tell their magnitude. So the idea here is one time somebody owed me money and I looked at the number. It was this number, and I didn't put a comma in it. And I was like, you owe me $11,000. And do you think they were very happy to hear that? No, because in fact, how much did they really owe me? Oh, but so you're telling me that this is not equal to 11,000? But it's only a difference of a zero. I thought zero was worth nothing. No, zero makes a big difference. If you had 11,000 in your account and they dropped one zero, you'd be pretty mad. And it would be 10 times smaller, wouldn't it? Because when we multiply by 10, we just conveniently put a zero on the end. Now, a lot of these numbers that we've been using exponents for, 2 to the fourth power, we go 16. Well, what if I had a really big exponent? What if I had 2 to the 100th power? Let's see what happens when we go 2 to the 100th power. 2 to the 100th power. Oh my gosh, wait a second, that number looks really small. You're telling me that 2 to the 4th is 16, but 2 to the 100th is only 1.267? I keep going because I don't want to round. Oh, the E is for exponent. So you're telling me this is the same thing as 1.26 to the 30th power? No, it's not. But E is for exponent. It's the exponent on the 10. So really this number is actually 1.267, okay, I'm not going to round, 65, I'll round now, times 10 to the 30th power. That's written in scientific notation. Basically, what my calculator is telling me right now is that, hey, stop. 2 to the 100th power is way too big, and we don't have enough space to write it in. It's so big, it's beyond a million, it's beyond a trillion, it's beyond a quadrillion, it's beyond a quintillion. In fact, I don't actually really know what it is, so we'll have to figure it out. Okay, so recall. Let's talk about the powers of 10. That was just my fancy example. 10 to the first, we already know is 10. 10 to the second is, what's 10 to the third? 10 to the fourth? 10 to the fifth? And notice that the exponent corresponds with the number of zeros. That's why before you said a billion. Actually, okay, after 10 to the fifth would become 10 to the sixth, which is a million. That means that a million is a 1 followed by 6 zeros. 10 to the, let's skip. Okay, we're going to skip past 10 million, 100 million. We don't care about those. Although I would care. Okay, if I had that much money, I would care. But we're going to go by threes. Next one, 10 to the ninth is a billion. 10 to the, what would come next after billion? Trillion? 12th is a trillion. So now you all know when you become trillionaires that you will have 12 zeros after your one. Okay? What does anyone know what comes next? Yes, it'd be quadrillion. Trillion. Okay, so really we're talking, you know, two sets. Not even two sets of quadrillion. I mean, a quadrillion times a quadrillion would be 10 to the 30th power. And I don't know the name for that. It goes quadrillion, quintillion, sextillion, septillion, octillion, nonillion, and then I don't know after that, okay? But you can see that those are kind of like, it's kind of like geometry. Octagon, octillion, right? Nonagon is a shape with 9 sides. A nonillion is a 1 followed by a lot of zeros, like way too many for me to keep track of right now. So anyway, you can look that up. These are just place value, talking about place value. What about what about 10 to the 0 power? It's the ones place. This all of the powers of 10 correspond to our place value. That's why our place value, does anybody know what our place value system is called? Base 10. Binary code is base 2. But our regular place value system that we all use for our money is called base 10. Place value base 10. Okay? Yes, clock, sure, yes, probably. Don't ask me too much about that. I can't think of that right now, but yeah, maybe we'll get there. Okay, 10 to the first. Does anybody know what this one is? Or 10 to the negative 1 would be 1 over 10 or a tenth. These are decimal places. 0.1 is a tenth. 1 over 100th, this is 0.01, a hundredth. Okay? 1 over 1,000 is, yes, a thousandth. Thousandth. And 1 over 10,000, because there's the 4 zeros. How many decimal places is that? How many zeros do you have in 10 thousandths? If you count the 1 in front of the decimal, you would still have 4 zeros. You know what I mean? But you have three zeros in front of the 1. So, yes. Right. So this is going to be a 10,000 and 1 over 100,000, 0.1234, 1. So there's 5 zeros if you count the 1 in front. And we really should write a lot lazy Americans as we are, we do not often put the 0 in front of the decimal as well. So let's do that so that way we can count it. We can say, well, that's 5 zeros because I have 1 in front of the decimal. Okay, so what is the pattern here? The exponent tells us we use this idea of scientific notation. The definition is that we can write every number as something between 0 and 10 multiplied by a power of 10. Here are some examples. Okay, so here, if I'm saying, well, I have 3.18, I only have $3.18, but I have it times 10 to the 5th power. So we're going to move the decimal. Yes. Why are we only going to include, I noticed how you said that you would include 3 zeros. Why 3 zeros? I thought it was 5 zeros. What's going on here? Ah, 5 places. We're moving it 5 places, so it became 1, 2, 3, 4, 5. 2 of the places were taken up by numbers. Okay? There's no decimal there, sorry. That's a comma. Here, 9.8 times 10 to the 7th. So how many zeros will I put on? Oh, so now I have, instead of $9.8, I have $98 million. You see that? That's a big difference, right? And a 0 makes a big difference when it comes to place value. That's the whole point, is if I'm a scientist and I'm up late at night burning the midnight oil and I'm writing these numbers, if I miss a 0, that's a big time problem, isn't it? Okay? That's why we have scientific notation. Now these ones, anything that has a negative exponent, what do you know about the numbers that are going to have negative exponents? They're going to be, yes, they're going to be very, very small. Big numbers have positive exponents. Small numbers have negative exponents. So now if I want to put this in standard form, I'm going to move the decimal how many places and which direction? I'm going to make the number smaller because I have a negative exponent. So negative exponents are very small. I'm going to move it 1, 2, 3. Now remember how I said I want to have 3 zeros. So if I put 1, 2, 3 zeros, 4, 4, 1, if I put the decimal right there, I've moved it 3 places, right? So I want to have that. If I want to keep consistent with my numbers and my number of zeros, then I can always take, I want 7 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 1, 6. Put the decimal after the first 0 because I had to move it backwards 7 places. The 8 took up one of those places. 1, 2, 3, 4, 5, 6, 7 is where the decimal goes. So there's 6 zeros after the decimal and 1 0 before. Okay? How do I put this number in scientific notation? Well, if I have a really big number, to put it in scientific notation, I would need to move the decimal. Well, where is the decimal? I don't see a decimal here. Where's the decimal? It's at the end, right? I want to move it so that it's right behind the first digit. So I'm going to write 3.42 times 10. Everybody see where she got the 6 power from? Yeah, 3, 6. Okay, I'm going to move the decimal. The decimal is here. I need to move it to right before I get to 5. So I have 5 times 10 to the 9th power. I have 5 trillion. I have 3 million. Oh my gosh. I have way less than a penny here. Way less than a penny. Not even a, I mean like a minute crumb of a penny. Okay, if I were to cut a penny into maybe millions of pieces or something. Okay, so where does the decimal need to move to? So, yep, 1, 2, 3, 4, 5, 6 times 10. Is that times 10 to the 6th power? Is that correct? Negative 6 power. How do you know it has to be negative? The number is, yes, you would feel very negative too if that's all the money you had in the world. Okay? What about this one? What's the decimal part going to be? How many places did we have to move the decimal? So I have negative 3. Why do I have a negative exponent? Because my number is very small. Now, I'm not good with left and right. I'm working on it, okay? So I don't like to say move it to the left, move it to the right, because most of the time I will be wrong. Well, half the time I'll be wrong. 50% of the time I'll be wrong. So I don't like to talk about left and right. I like to talk about big and small. My number is really small. I have a negative exponent. My number is really big. I have a positive exponent. Move it whichever direction makes sense to get that number that you need. You know what I mean? So small numbers, negative exponents. Okay. We have a word problem. It's also much easier to multiply numbers together once they are in scientific notation. We'll see this in some applications below. Light travels at approximately 3 times 10 to the 8 meters per second. So that's really what? Is that very fast? 3 times 10 to the 8th. Does anybody know what number that is? Comes right before a billion. 300 million. That's 300 million meters per second. And there are approximately 3.15 times 10 to the seventh, seconds in a year. How far does light travel in 1 year? What would you do? Scientifically, I like that. Scientifically notated numbers. That's good. 10 to the 7th. So we could use our laws of exponents, can't we? What would the, so we're going to do 3 times 3.15, right? We can multiply those. This is the commutative or associative property of multiplication, times 10 to the 8th times 10 to the 7th. I don't know why I wrote that 10 so funny. So what is 3 times 3? 9.45. 9.45 times 10 to the 15th. Does everybody see, where did we get the 15 from? Does anybody play cribbage? So that's why you knew that 8 plus 7 right away is 15. If you play cribbage, you would know that. But you might know that anyway just because you know how to add. So, all right, the distance from the Earth to the star. Oh, we probably should, since it's a word problem, we should write this in words. But anyway, this is what? Meters? Yeah. Well, the meters per second, the seconds and the seconds actually cancel with each other, leaving just meters because that's how far. Yeah, how many meters in 1 light year? Light travels. Okay, you would put it into a sentence. The distance from the Earth to the star, how do you say that? Spica is 2.2 times 10 to the 18th meters. Wow, that's a lot, right? We even know that's probably beyond our quintillion. How many light years is Spica from Earth? Oh my gosh, how do we do this? Yes. 17 zeros, okay. But what operation are we going to do with these two numbers? If we want to know, like this is how many meters is a light, wait. This is how many, wait a second, the distance from Earth. Okay, let's draw a picture. Here's Earth, here's the star, okay? And we know that that distance is this amount of meters. How many light years? Well, we said, how many light years? Light travels at approximately this many meters per second. There are approximately this many seconds in a year. Isn't this a light year then? Isn't that what we calculated, you guys? So divided by 9.45 times 10 to the 15th meters. Okay? Is that wrong? In 1 year. So wouldn't that count as a light year? I don't know. You guys will look on the key for these as well. But let's just divide it like this for now. We'll go check it in a minute. Okay. It's getting late. We've been doing math for a really, really long time. Does everybody understand that? Okay, good. Okay. So let's say we divided this and we have 2.2 divided by 9.45 equals 0.23 times 10 to the third. And now I want another decimal point. 2. Okay, so take this with a grain of salt. If we multiply that out, what does that give us? 2. I'm actually getting the number, right? This would be how many light years? 232 light years is the distance. I don't know. We'll look that up. In chemistry, a mole, also known as Avogadro's number, right? Avogadro, is the number of hydrogen molecules in 1 gram of hydrogen. This number was determined by taking the charge of a mole of electrons, approximately 96,500, and dividing it by the charge of a single electron, approximately this. Use scientific notation to determine the approximate value of Avogadro's number. Okay, I'm going to let you guys look this one up on the thing. Or do you want to tell me how you would do it? What would you do? No idea? All right. I have to read it again. It's so much reading. Oh my gosh. All right. In chemistry, a mole is known as this guy's number. It's the number of hydrogen molecules in 1 gram of hydrogen. The number of hydrogen molecules in 1 gram. The number was determined by taking the charge of a mole, approximately 96,500, and dividing it by the charge of a single electron. They told us to divide, right? Am I interpreting this correctly?
Yeah, that's correct. What I did is I
Yes.
the charge of a single electron by
And you know what? It's really cool. Some things are really fun to do mentally, and other things are not. But one thing I'm going to show you right here is if I use the calculator for this problem, because I don't really want to mentally divide these, I would need, the important thing here is to make sure you put parentheses. Okay, because if I don't put parentheses around that, I'm not going to be dividing by that number. To the negative 19. Now it's also important to use the negative symbol. So now I'm going to go out of the parentheses, out of the exponent, close the parenthesis, and we should get this. Equals 6 point. Oh, you see it's not 6.0237. I rounded. E to the 23rd is times 10 to the 23rd. Use scientific notation to approximate the value of Avogadro's numbers. That would be it, right? Check the key. You have all the keys for these, especially this light year one. That was kind of wrecking us and not too sciencey.